Hello and good day once again. In the last video, I've created an arithmetic logic unit which does addition, involving 4 bits. In this video, I'm going to create an arithmetic logic unit in Circuitverse which both does addition and optionally subtraction. I have here already created for us the previous circuit which does addition. We are just going to convert this into something that will convert into a subtractor given a sub command. For example, uh, if the sub command or the sub input is 0, this will just perform addition. Otherwise, if the sub command is 1, it will perform subtraction. So we will have to remove this first input because this is useless. And then we will have to extend our inputs to make way for more gates. That is because we are going to use a special gate that will convert, okay, b into 1's complement. Now remember that in binary, addition is done by 2's complement, rather subtraction is done by 2's complement addition. And it is important to note that when subtraction is done, we should first convert the item b into 1's complement before adding 1. So the question is, how do we convert into 1's complement? Now, since this is optional, we should use another input, which we will call sub, with direction to the left. We'll label this as sub. When sub is high, it will convert b into 2's complement. But first, it should convert b into 1's complement. How do we do that? Let's remove the connections to b first. We know where they are. Each bit is converted into 1's complement by an XOR gate because a 0 XOR 1 is a 0 XOR 1 is a 0, okay, and 1 XOR 1, no, 0, sorry, 0 XOR 1 is a 0 and 1 XOR 0 is a 0. Is that correct? Let's try that anyway, no? Using an XOR gate with a provisional output. So let's put an XOR gate. Let's put this downwards and let's connect this to a provisional output, which points upwards. Okay. Let's connect the first input to B and the second input to sub. Okay. That's an XOR gate. Now when 1 is XORed with 0, it remains the same. 0 is XORed with 0. It remains 0. 1 XOR 1 remains 1. But when sub is 1, okay, 1 XOR 1 is 0. 0 XOR 1 is 1. So when sub is 1, it will convert B into 1's complement. When sub is low, it will retain B in its normal form. Which means that when sub is 0, it will do an addition. But when sub is 1, it will do a subtraction. Our only problem here is we are only converting into 1's complement. How do we add 1 to the 1's complement? We can also do that by connecting sub to the first carry of the first full adder. That's why we are using a full adder, because we can use that for subtraction. When sub is 1, the needed 1 that is added to the 1's complement is added to the first adder. That's also the technique when converting from 2's complement into normal form, or from normal form to 2's complement. We use the XOR gate to convert it to 1's complement, and we use an adder to add 1 to the least significant bit. So what we are going to do now is just going to repeat this process by using XOR gates. Point it downwards. I hope we can copy this. Yes, and then we just paste it here also. So we have it here. Okay. We'll connect the first input to B, each one of them. Okay. Yes. We also connect to B. Okay. And then all the rest, the second input of the XOR gates, will convert. Will connect to sub. So what happens here is when sub is 0, B will be the same. Anything XORed with 0 is itself. Okay. And then we'll now connect the output to the real output. Trim the unimportant lines. Okay. Which makes us ready to test the full adder and subtractor. Okay, let's enlarge that. Now, for example, we will have 9 or 9. That's 9. 1001. We'll add it with a 1. Okay, it becomes uh, no 0001. 1 plus 9 becomes 10. So 1010. Okay, but when subtraction is high, what happens is, okay, all the b's are connected into 1's complement, and the first full adder is added with a 1. So 9 minus 1 is 8. It becomes an 8. Okay. If you will wonder what will happen if we'll reverse the process and say 1 minus 9. Okay. So the answer is 0111. But this is the 2's complement of 8. So the answer is still correct, but it's in 2's complement form. How do we know that it's in 2's complement form? We'll just convert this to 1's complement, which is 1000, which is 1248 plus 1. This is 9. I'm sorry. This is 9. No, 9 minus 1. We forgot that. 9 minus 1 is 100, which is the 2's complement of 8. Because this becomes 01111 and we add 1. Okay, I forgot the 1 there. That's why I made a mistake. Anyway, this is 8 in 2's complement form. When we say 9 minus 0, this is the 2's complement of 9. So therefore, this is still a correct adder. The only problem is when the subtrahend is bigger, or the minuend is bigger than the subtrahend, the result is in 2's complement form. In the next video, we are going to discuss how the negative form can be detected in a full adder using the ALU provided by Circuitverse. Okay, I hope you see the point. This is an example on ALU with adder and subtractor, where addition or rather subtraction is optional, given a command called sub. We will connect this to a negative sensor in the Circuitverse ALU in the next video. Thanks for watching and see you then.